recording? So AC synchronous motors. As the name suggests, this is quite different from the asynchronous motor. The difference being that its RPM is almost the same as synchronous RPM.
What does that mean?
In the previous topic, asynchronous motors, we saw that there is a synchronous frequency at which the motor is running like completely in phase with the stator frequency and it's making zero torque. But as it makes more and more torque, like if you look at the diagram, so if you look at this diagram, which is the torque versus RPM graph of an asynchronous motor,
Mm.
at 100% speed, which is synchronous speed, it is
Mm.
making zero torque. And as it goes a bit to the left, where there's a little bit of slip, let us say 92 to 95%, in that region will be the nominal region.
Mm.
And if you go further to the left, you will find the breakdown torque where torque is maximum. But here, because of the high slip, we are having a lot of power losses. So this is not used for long period of time. But if you contrast this with a synchronous motor, it will just look like almost a perfect vertical line at synchronous frequency. The torque varies along the same line itself and the current consumption changes accordingly.
Okay.
So that means that there is no self-regulating property. I will get to that. So, oops. So here, like I mentioned, the shaft speed is fixed by the line frequency. So you to change the RPM, you have to change the frequency of the AC supply itself.
Okay.
It's heavier and more complex, needs more like sliding elements like brushes and slip rings, which is a disadvantage. But there are ways to overcome it. We will look at that. It has double excitation usually. So the stator is excited with AC and the rotor is excited with DC. We do this because stator is running on three phase, and three phase means you need to have three wires, but the DC just needs two wires, and it's also carrying much lesser power. So what we do, we have the DC on the rotor side so that we can have small slip rings which don't have to carry that much power, and that too only for two wires. So that helps to decrease costs. So that's what I've explained here. That's why we excite the rotor with DC and stator with AC. It has very high efficiency and like big synchronous motors in the order of like hundreds of kilowatts. The efficiency is above 98%. It's almost 100% efficient, which is why electric vehicles are using synchronous motors. The generators mostly are synchronous. Like even in normal petrol vehicles, the alternator part of the engine, which is making electricity to charge the battery, it's also synchronous. So let's
Just
look.
one question.
Yes.
Like in terms of the design, can you tell me what the rotor and the stator is?
Yeah, we'll look
Like,
at it in the right next slide. So these are two different types of like DC synchronous motors. So here what we have, the stator is excited with three phases. You can see them in yellow, black and red. And the rotor, this is the part which is going to rotate. It's basically the whole outer can of the motor is going to rotate. And on the inner side of this can, like that's the can, on the inner side there are permanent magnets. So we replace this DC excitation of the rotor with permanent magnets. This limits the power, but it enables like lot of simplicity because now you don't need any slip rings, no brushes, there is no DC excitation needed. So it simplifies a lot of the parts. That's why small like model aircraft they use these motors. But nowadays these motors are being used more and more commonly as magnets have improved a lot in recent times. Earlier there were not good strong permanent magnets, but now there are. So even I think wind turbines which make megawatts are using this technology with permanent magnet excitation. Here on the top right you have a more classical example where the rotor also is excited with DC. So you can see these wires. So the dot indicates the wire is coming out, like current in the wire is coming out, and the cross indicates the current in the wire is going in. Like think of it like a bow and arrow. If an arrow has penetrated through, like at the at the rear of the arrow there are fins, right? Imagine it's paper and the arrow has gone through it. If the
Hmm.
arrow has gone through from us into the paper, then it will create this X because of the fins. But if it has come out, like, but not completely, then it creates these dots. So that's a good way to remember which one means what. So X is going in, the dot is coming out. Or is it? No, I think this is correct. So that's a DC part, and on the outer side you have the stator. The stator is AC. Construction wise, it's a little bit different because now you just have coils. You don't have the squirrel cage with the with the sheets, enamel sheets in the middle to improve the magnetic field, but you have just coils with these cores to improve the magnetic field strength. So is that sufficiently clear?
Yeah.
Okay.
Yeah.
So now let us look at the basic circuit, how we represent synchronous motors. So this is the representation of one phase of the synchronous motor. So there are three phases and each of these phases are going to look very similar. So we just
Hmm.
look at one phase at a time. This UP, what we see here, is called pole wheel voltage or excitation voltage. It's a DC, doesn't change. It is somewhat similar to the induced voltage we saw in DC motors, if you remember.
Okay.
It's somewhat similar to that in that, like, the faster it's spinning, the more back EMF is induced. Similar story here. The load angle beta is the angle between the stator frequency and the rotor. So let's go back here. So like I mentioned previously, these stators, this three phase arrangement, they work together to make an effective phasor. Right, this is the effective magnetic field, and with time this magnetic field also rotates. It has an omega, and it also rotates with the same 50 hertz frequency. And this rotor, it's physically rotating, right? So if you mark two arrows, like, just imagine that the rotor has an arrow on it, and the phasor, the effective magnetic field phasor is being tracked. The angle between these two arrows, so the angle between the rotor and this magnetic field, which kind of implies like how much the rotor is lagging behind the magnetic field, that is called beta. So if you overlap these two and you compare, so it's lagging behind. So this is beta, this is the rotor, this is the stator magnetic field. And there are limits to how much this beta can become. So under no load, when there is no torque being made, there is no reason why this rotor will lag behind the stator. So it will be perfectly in sync because friction is almost negligible usually compared to the power the motor is making. So it will be almost 0 degrees in real life. Theoretically, we can take it as 0. And in the extreme case, it will be minus 90, like it will lag behind by 90 degrees. If it lags behind any further than that, it will go completely out of sync and it will stop spinning, I think. Or it will stop making power. Basically, the stalled condition, overload. So it's beyond what the motor can provide in terms of torque. So that is the load angle. The torque produced is proportional to sine of the angle. So this is the equation for torque. We will look at the currents, but for now just look at the relationship with the angle. So sine of minus beta is proportional to torque. The more the angle beta you have, modulus, like the absolute value, the more beta there is, the more is the torque, but some other stuff also changes. Now let us look at the current
Mr.
terminology. I phase is the phase current or rotor current. No, stator current.
I want to ask you one thing.
This is stator. Yes.
My question is like in most of the questions and exercises, the basically the voltage is given as nominal voltage and current is given as nominal current. So I also have this question like in terms of DC and AC asynchronous as well.
Hmm.
Like i- is the nominal voltage you terminal voltage or the
Good
or the
question.
phase?
Good question. I will show here.
And also clarify for the nominal current, because
So
some of questions I attempted, I somehow got the answers, but most of the questions you gave in the exercises or in the lecture slides, my answers were different.
I see.
And
Okay. So in DC, it's quite simple. Nominal is just the supply current. Like nominal power is output power. Nominal power is output.
which is mechanical power.
Yes. Nominal voltage or current is the supply side. In DC, it's very simple. There is no complication because there is no gamma or Y or delta connection in DC. But in
Supply
AC,
side, what do you mean?
if you have this star or Y connection,
Mm-hmm.
that means the voltage that each phase is getting. So V phase equals V nominal divided by root 3. I phase equals I nominal.
In AC, Y connection. Okay.
But in delta, it's the other way around. I phase, like here, what I mean by phase is one phase of the motor. So this is one phase, one element. So I phase equals I nominal by root 3, but the V phase equals V nominal.
Again, but in the equations we have terminal voltage and induced voltage.
Induced voltage is not affected by all this. It's the same, right? Because it's internal to each phase in the system. So induced voltage is not affected. But if you're thinking
Induced
about,
voltage is basically phase voltage.
no, induced voltage is the back EMF. So like as the motor, especially in DC, as the motor spins faster and faster, the rotation itself creates a back EMF in the circuit, which decreases the amount of torque that can be made. So like
Okay.
that's what I usually talk about, right? You have the resistance, armature resistance, and then this is the VB or U induced back EMF. So as you try to spin it faster, the rotor, the coil of the rotor is rotating so fast that voltage is being induced as per Maxwell's law, d phi b by dt, because the same magnetic field, but you're rotating it faster, so the rate of change is higher, so more voltage is induced, which means the current will decrease, meaning you will make lower torque. I mean, this is a simplified explanation, but in general, this is what is happening. So that is
Okay.
not affected with all this like delta or star. What is affected is the actual voltage that the motor gets, or like each phase of the motor is getting. So if you do this process, you will be fine. So so back to the current term. So far I have explained what is the load angle beta, what is the pole wheel voltage. It's similar to the induced voltage, right? So the pole
Yeah.
wheel voltage changes during the course of the operation as the RPM changes. ISC is short circuit current at 0 RPM, which means it's like max torque kind of. It's at 0 RPM, the rotor is completely stopped, and what's the current being consumed? ISC 0 is the short circuit current at no load, which means it's spinning completely freely, beta is equal to 0, and there is no UP because there is no lag between the rotor and the stator. Like this beta angle goes to 0, right?
Yeah.
Beta goes to 0, which means there is now rotor spins fast enough to avoid, like, fast enough that it doesn't see a change in the magnetic field, that it sees no d phi b over dt, right? So which means there is no induced voltage and up goes to 0. Some more formulae. U is the supply voltage, so which we saw here. U is the supply voltage and there is the current flowing, and up is the kind of like induced voltage, but here we call it excitation voltage. up plus j x1 I1. This j term is there because we are working in the complex plane, like real complex plane.
Mm.
So we have this j term, and I1 is the current flowing through that phase. Torque is
And
given here.
X1 is just the variable.
Sorry.
X1.
Yes, x1. Yes, sorry, I missed that. So x1 is reactance. Reactance is the AC equivalent of resistance. Like I mentioned previously, we have this thing called impedance. Impedance is the very general form of AC resistance, right?
Okay.
And it's equal to R plus X. R is the actual resistance, DC resistance, plus reactance. And this reactance is seen only when there is a frequency. When frequency is 0, there is no reactance. Zero frequency basically means DC. So this reactance is something which exists only in AC, and it's a byproduct of the, like, the inductances and capacitances that the motor component will have. So the motor,
R is resistance and X is reactance.
so to simplify here, I think we're ignoring the resistance, or it's included in the X itself. Not sure
Hmm.
about that, but it's the AC equivalent of resistance that you see in DC.
Okay, okay.
Here we have the torque expressed in two forms. Here in the first equation we have it expressed in terms of the power factor cos phi.
Hmm.
In the second equation we have it expressed in terms of the load angle beta. Electrical power is the power of all the three phases combined, right? Each phase is making U phase times I1 times cos phi. This U phase is same as U. And
ISC is short current,
there are
short
two
circuit.
ISCs. One is ISC and other one is ISC 0. ISC is short circuit current at 0 RPM. Short circuit
Okay.
current at 0 RPM. ISC 0 is the short circuit current at 0 load.
Zero load means there is no voltage, pole excitation voltage.
No pole wheel voltage, and basically that means there is nothing connected to the motor, it's spinning freely in
Okay.
real terms. So electrical power is very straightforward. Previously we saw that in a given circuit, to get electrical power,
Hmm.
it's just ui cos phi because it's AC and there is a phase shift. But since what we saw was for one phase and there are three phases, and this is already RMS power, we can multiply by 3, no problem. So that's how you're getting electric power is 3u phase I1 cos phi. Now we are looking at the special cases. up equal to 0 is happening at no load condition. So short circuit basically means like it's like a short circuit across the terminals of the supply. So U goes to 0. So this is at 0 RPM. So it's still the same equations that we had previously, just some terms become 0, so the equation simplifies and we are able to find the values of short circuit current ISC and ISC 0. So this is U by x1 and UP by x1. Yeah.
Okay.
We have a very useful tool called power locus diagram for synchronous motors, which really helps. It's something we are doing geometrically, we are drawing, and it helps us to get these values that are given in the that are required in the question. So let's do this example. Look at this example, see how it's done. Lossless AC synchronous motor. Most motors, like especially what in this 2500 kilowatt range, it's practically 100% efficient. It's
Okay.
quite close to that. Power factor is 1. No, number of pole pairs, sorry, number of pole pairs is 1. Frequency is 50 hertz, and the power factor is 0.85, which means it's running as a motor. If it was negative, that would mean it's running as a generator. P equals 1 at 50 hertz implies N naught equals 3000 rpm. This is the same formula that we saw previously. It's just the synchronous rpm. UN is 3000 volts, but it's in Y connection. So the U supplied, like, or U phase, let us say, is UN by root 3. Yes. Minus, I think beta is minus 25. That is missing here. Beta is minus 25 degrees. And nominal power is 2550 kilowatts. And we, using the curve, we have to determine all these, and the scale for drawing has been suggested. So the first step is to draw the phase U phase, which is, as we calculated, UN by root 3 because of star connection. And this U phase is the real supply itself, so we are drawing it along the real axis. In this plane, the real axis is vertical and the imaginary is horizontal. The current is on to the left of the U phase, so anti-clockwise angle positive. The phi we can get by cos inverse, right? Phi equals cos inverse of 0.85, because they said the power factor is 0.85, which is cos phi. And the vertical component, or like vertical equivalent of torque, is the nominal torque, because this phase current is at nominal operation, right? Un is mentioned, Pn is mentioned. So this phase current is at nominal operation. We can calculate that. How can you calculate phase current? What do you think? Hello?
By power?
Yes, through the means of power, exactly. So nominal power is given. So nominal power is given to us. Pn equals 3 times U phase times I phase cos phi. U phase we have calculated is U1 by root 3. 3 is given.
How how did you calculate uh, RPM? 3000 RPM.
The same formula as last time. So F is 50 hertz, right? So 50 times per second. So it basically means 50 rotations per second. So N equals 60 times 50, because 60 seconds per minute. So
Mm-hmm.
you have 3000 rotations in 1 minute.
And it will be nominal speed.
This is like always. There is no nominal, no breakdown speed. It's always at this speed. If the frequency is the same, it's going to be at this speed, irrespective of what load there is, until you stop it. Basically, like that's the short circuit case. So any
Yeah.
load which is below its breakdown torque, like the maximum torque it can give, it will be running at this RPM. So that's the special thing about synchronous motors. So they are not having the self-regulating feature which asynchronous motor had. In asynchronous motor, let's say you're using it to power a fan, right? If you somehow, like, there is some kind of obstruction or friction, and the fan is creating more resistance, the motor will slow down while consuming the same power, more or less, or maybe a little bit more power, depends. little bit more power, but here it will not slow down. It will consume extra current such that it is able to meet this new torque requirement and will stay at 3000 rpm. So that helps us in a way. It's quite powerful because you have perfect control over the speed if that's what you want. This is very well
Mm.
suited, which is why I think like trains and such, like the newer ones, they are using synchronous motors because then you have perfect control over speed. But naturally, this means you need a proper control circuit for regulating the speed, and you can't do it just through changing the load itself. So back to business. They have mentioned it's lossless. Usually, nominal power is output power, but here it's lossless. So P nominal equals P electrical.
Phenomenal means
P
P.
nominal is usually output power, mechanical output power, like we discussed.
Yeah, but lossless means that it is also the input.
Yes. So using the electrical power formula, we can get the phase current. So that we are marking that U phase is marked vertically, I phase is marked to the left or anti-clockwise to U phase with this angle phi, which we are getting from cos inverse of 0.85. The
Okay.
vertical, like the vertical component of I phase is the nominal torque, that is marked like this.
Okay.
Next step is to draw the pole wheel voltage. This UP is at an angle of beta from the phase voltage.
Mm.
And notice they said minus 25 degrees. In maths, angles that are anti-clockwise are positive.
Yeah, and clockwise or negative.
Exactly. So that's why it's to the right of U phase. But what we do know is it's going to be along this direction, but we don't know the actual length of it because we don't know how much UP itself is. We will find this in the next step. So now we draw.
One question.
Mm-hmm.
To find theta, I'll just cos inverse 0.85, right?
Yes, that is not theta, it's phi, yes, but cos inverse 0.85.
Okay. And then the UP.
UP beta is given, the load angle is given minus 25.
So we want like calculate it and mark it just a dotted line.
We will mark it, but at this stage in the drawing we do not know the value. So as we proceed further,
Okay.
you will find what it is.
Okay.
So that's why it's a dotted line which we extend out because we don't know how long it actually is.
Okay.
Now this short circuit current ISC is drawn perpendicular to UP. Like if you're doing it on paper, just imagine you have a scale, right? You take it perpendicular to the UP line and you move it along the UP line until one end of the scale is on IPH. Then you extend until it
Mm.
meets the imaginary axis, and that point is of interest to us later on, you will see, but it's
Okay.
very important. And that point that point is basically showing the ISC 0 current.
Okay.
And note the directions as well. So IPH is pointing outwards, ISC is pointing towards this center, and ISC 0 is also pointing towards the center. That's because of vector rules. IPH plus ISC is ISC 0, like law of vector addition. And why is ISC perpendicular to UP, you might ask? So ISC is perpendicular to UP because it is occurring at synchronous RPM. What did we say? ISC is no, that's not ISC. That's ISC 0. Okay, that's not a good explanation. So we did that. We got this center,
Yeah.
and now with ISC as radius and this point as center, draw a circle.
Okay.
So naturally, since we took this point as center and this length as radius, it will pass through this point, this corner point, and it go through it almost all the way, so. Like we don't need stuff to the right of the vertical part. So till somewhere here roughly is sufficient. And from this center point, take a line vertically up, and that is giving you the breakdown torque.
Okay. Okay.
And we know the nominal torque because we know the nominal power, right? So using first law of drives, you can get nominal torque, and then if you measure
Okay.
this length and measure that length, do a ratio, you can get the breakdown torque. Also notice UPH,
Like,
like there is
by,
no,
you mean by getting you mean by getting the breakdown torque by like measuring it to the scale?
yes. So
Okay.
Tn equals Pn by
And
2 pi n. N also we know it's n naught, right?
yeah,
And then you measure Tn's length, Tbd length.
yeah.
Like let's say this is 2 centimeters and this is 5 centimeters.
Mm,
And
mm,
this diagram is drawn to scale. So
mm,
Tbd equals 5 by 2 times of Tn.
mm,
Yeah.
mm, mm.
This is the last step, I think. So we draw this final line Jx1I1, which is perpendicular to the IPH line,
Okay.
because this I1 and IPH are the same actually. This is also I1. And multiplying J in the complex plane makes that line perpendicular. So x1 is like just a real number. It doesn't do anything. It will just scale it. So if it was 2 and 2I1, it will be in the same direction, just twice the length. But because there is a J term, it's perpendicular now. So draw this perpendicular line such that it's perpendicular to IPH and it passes through the tip of UPH. And wherever this line intersects with UP, that is your pole wheel voltage value. Sorry. See? So that is UP. This is JX1I1. And notice again, vector law of addition is working. So earlier we saw this equation UPH equals UP plus JX1I1.
Mm,
UP plus JX1I1 gives me exactly UPH in vector terms.
mm.
So by making this drawing, now you know everything about this asynchronous, about this synchronous motor, and you can get the required stuff. So mainly
Okay.
what was asked, ISC 0, we got that. Breakdown torque, I showed you how to calculate that. Pole wheel voltage, we got that as well. Note
Mm.
that all the voltages will have the same scale, all the currents will have the same scale, right? And since we are drawing multiple quantities on the same graph, different quantities will have different scales. So the whole graph doesn't have a single scale. So the graph is just marked in centimeters, but each quantity has its own scale, like how many volts per centimeter, how many amps per centimeter, and so on. Sometimes it can be given, otherwise you have to choose some realistic number which gives you a decent looking diagram which fits on the space given. So that is all.
Okay.